And our department, as I mentioned, is also very diverse. So we have people from operations management, strategic management. So we are a very diverse group, let's say.
I will be gentle.
Sounds good.
I just want to give a big welcome to Richard McAdock. You know, this is a series that Maria and I put together, I guess it was last year, the year before, as a way to sort of supplement what our PhD students are learning in the classroom. So this has been nice to bring in some leading scholars. But it's been great to get folks in like Richard to teach us some, you know, kind of what's on the leading edge of empirical analysis, and we've had some really great sessions. And I want to firstly thank Maria for all of her hard work, not only in identifying great people to come in, but also organizing the sessions and getting the word out to our faculty and students. So thanks to Maria for that. Thanks also, of course, to Richard for sharing his time with us today. As you probably all know, hopefully all know, you know, Richard is one of the thought leaders in strategy these days. He is currently a professor of management and the Brock Family Chair in Strategic Management at Purdue's Krannert School of Management. He received his PhD and MBA from the Wharton School and an MA and BA in economics from Yale. He's, at least from my standpoint, he's best known for his 4 theories of profit framework. If you're not familiar with that, I encourage you to read that article where he, I guess, laid it all out, probably in that journal management article a while back. But it's really a great way to sort of think about, you know, how firms sort of, you know, what mechanisms allow them to be profitable. And it's a really nice way to sort of approach thinking about not just strategy, but entrepreneurship as well. You obviously are familiar with probably a lot of his work, but you know, he's very well represented in journals like AMR, Man Science, and Strategic Management Journal, where I think he's published a dozen or so articles. He's been honored by the Academy of Management Review and the Academy Management Conference for his research. He's won several awards. He founded the Atlanta Competitive Advantage Conference, which has been a long-running place for really groundbreaking ideas around strategy. And before joining Purdue, he was at Emory and at Tulane before, where he began his career and has also won numerous teaching awards. So not just a great mind, but a great teacher as well. So we're really thrilled to have Richard here with us today. We look forward to learning a little bit more about modeling, and I'll let Richard take it from here. So thanks very much.
Thank you very much for the very kind introduction, Scott. I really appreciate it. And thanks to both you and Maria for organizing this event. Thanks to the Field Center for funding it. And thanks to the various members of the Baruch community for joining us today. So let me just start off by asking each person here to maybe just give us a quick introduction and tell me a little bit about what your interest in formal modeling is, why you might be interested in it, so I can get some sense. Do I want to go first? Maybe Maria, you can kick us off, huh?
Sure. Of course, my name is Maria Halbinger. I'm in the innovation/entrepreneurship area in the management department. And my interest in formal models is a very specific paper that Richard already knows about. It's on initial coin offerings. And the reason why I'm interested in this one is because we collected data and we would like to talk about something where we don't have a complete data set. And so my hope was to learn more about how we could perhaps through a formal model make some kind of predictions or theorize about something where we don't have the full data yet, and perhaps have a nice, I don't want to call it workaround, but basically have a more valid, solid way of arguing and bringing the paper forward. I don't know if that's something that would work, but
yeah, I think, the one of the values of formal modeling is that it allows for more of a division of labor in the academic enterprise, so that some of us who maybe are more inclined to work with ideas can focus on that, and leave it to others to to dig into the data and see if those ideas make sense. Rather than having to create a new theory every time you come up with a new data set. So I think that's a very good use of formal modeling, is to make predictions that you can then take to the data, right? And then that one nice thing about formal modeling is that the assumptions on which your predictions are made, right? Often in the more informal forms of theorizing, predictions will be made, but it's not entirely clear what all the assumptions underlying those predictions are. And so it's not entirely clear what the boundary conditions on those predictions are, what assumptions might be violated in what cases. And so that's certainly one real benefit of formal modeling, is to have a set of predictions that you can bring to the data that on which you are pretty certain what the underlying assumptions are. Okay. Scott, maybe you could do next. Tell us what
you're sure. Thanks. So Scott Newbert, I am in the management department as well, on the entrepreneurship faculty, and I think Richard articulated pretty well what I've been sort of kicking around in the back of my head. I'm probably more on the theoretical than the empirical side, but one of the things that's frustrated me for a while is sort of the looseness of how sort of theorizing has taken place in and around entrepreneurship, I would say, in particular. And so I'm looking to add a bit more precision to the way in which theory is developed, or where theorizing takes place. And so that's my main interest, is to try to tighten up some of the what I see as sort of loose ends in theorizing as it seems to be taking place now.
Right, that's good. Yeah, similar sort of motivation to Maria, to just kind of know why we are able to predict what we predict, right?
Yeah.
We want to. I remember the famous mutual fund manager Peter Lynch, in his book on investing, wrote, "Know what you own and know why you own it." And this is similar. It's know what know what you're theorizing and know why you're theorizing it. Absolutely, or know what you know and know why you know it. Yeah. Nikisha, can you tell us next what your interest is in formal modeling?
Yeah, sure. So I'm Nikisha, second-year doctoral student, interested in mergers and acquisitions and why they fail. And I really like the formal modeling because I'm interested in making a theoretical contribution. And so looking at this, I think this will help me kind of organize my thoughts, frankly, and just kind of figure out how to better develop my ideas and theory, but also having that connection to the empirical component of it. And so I find this very interesting, and thank you for the papers that you sent along by Philippe and the other folks. It's a really good background just to kind of, and what was interesting actually, I didn't realize some of the papers that are mentioned in their work are papers that I've read, but I didn't realize that was formal modeling, or what that is considered a formal modeling paper. So thank you for passing those along.
Yeah, sure. So, I mean, M&A obviously is a very well-plowed field in the field of strategy, right? Lots and hundreds, if not thousands of studies on M&A. And I think that's one place, one reason why it's beneficial to use formal modeling in situations like that. Because in some sense, I mean, the low-hanging fruit, when you're starting to study a new topic, a new phenomenon, whatever, the low-hanging fruit is fairly easy to get without formal modeling, with just kind of informal theorizing. But when you're studying something that has been studied in detail, over many decades. Making a contribution to theory requires you to reach up to the upper branches of the tree, where the fruit hasn't yet been picked. And formal modeling maybe provides a little bit of a ladder to help you reach up to those upper branches and get some fruit that no one has reached yet. Okay, great. Elena, can you tell us a little bit about what your interest is?
Sure. I think this is coming from my training in the doctoral program, why I'm interested in this modeling, primarily because I remember, I think it was Rich Burton or Will Mitchell, one of them, saying like, the more tools you have under your belt, the more questions you can answer.
Mm-hmm.
So it's, every time that I thank Maria and Scott for leading this opportunities to, learn new methods and learn new ways of answering questions, because I think we tend to be too ingrained in like, okay, I do empirical and there's a limited number of questions that you can answer. And to your point, I think there's a huge benefit for scholars to be able to really tease out the mechanisms and in strategy dealing with heterogeneity and all these other things. It's empirically sometimes it's not possible to do those things. So perhaps creating some more mixed methods and diving into different ways of answering the same question, I think it's beneficial. So that's why I'm here.
Right. Yeah, and I like your point about when you're doing empirical work, you're limited in terms of what you can say by your data. So you're kind of in a narrow part of the battlefield. I use this metaphor of, I like to think of theory as being, in terms of a military doctrine metaphor. Theory is the high ground that looks over the battlefield, right? And military doctrine says you always want to capture and hold the high ground. And there's good reason for that, because when you're down there in the quagmire of the battlefield, you're limited as to what you can do, right? You can only attack what's right in front of you. And you can't see threats from a distance, right? You can't see threats coming at you from a distance. But when you're on the high ground, you can see further. You can see the entire battlefield. You can attack any part of the battlefield, right? And you can also be a little bit better protected from attack, because any attacker is going to have to be coming uphill at you with all their equipment and weighed down, right? So anyway, that's why I kind of think of theory as being kind of the higher ground of any academic field. It allows you to attack more topics than you could otherwise, and to not be limited.
Your background too.
Pardon?
It matches your background too.
It matches my background. Yes, I'm up there in the clouds on that mountaintop. Exactly. Yeah. So okay, good. Thank you, Elena. Let me see, who haven't I gotten to? Jung-hoon, what's your interest in formal modeling?
Hi. Thanks for this opportunity for me to learn about formal modeling. So I'm a PhD candidate, a third-year PhD student at Brook, and I'm interested in basically corporate sustainability and more of a strategy design. And one day I remember, like a couple of years ago, back then I was interested in strategic alliances and the exploration versus exploitation, like in the context of organizational learning. And then one SMJ paper drew on the formal modeling, and then I had no idea what's going on here. So, okay, although I may not use this formal modeling for my own study, at least I need to have some knowledge to understand what it is, so that I can, make some contribution to the field. So that's my one reason. And as Elena pointed out, as I know more like methodologies, in addition to what I have known so far, I think I can expand my horizon in my research project.
Right. I think that's a good point. And even if you never use the formal modeling techniques, it's good to know how they work. I mean, I may not do empirical research using QCA or using structured equation modeling or anything like that. But the fact that in my doctoral program, I had to work through some exercises using those methods means that I can be a more informed consumer of research that uses those methods, right?
Right.
So I think it's beneficial to at least be able to understand, the basics of formal modeling so that you can, maybe you can't replicate those models yourself or improve upon them, but you can at least understand a little bit about what went into making them and where their limitations are. Yep, I agree. Let's see, who haven't I gotten to yet? Jared?
Yeah, good morning. So at Academy of Management, I hang out with the SIM and OMT crowd. I'm interested mostly in theorizing individual level moral mechanisms and how morality works in the market. So my theorizing is more at the individual level and trying it on with different moral mechanisms. So I'm just here to learn. I haven't really done much, so thanks for this opportunity.
Well, that's neat. I mean, I really haven't heard of anybody applying formal methods in that space. So you actually have the opportunity to be a pioneer here if you wanted to. I don't see any reason why you couldn't apply formal modeling logic to that topic. Obviously, one of the things that formal modeling is excellent at addressing is trade-offs, between competing objectives or competing competing interests between people or competing objectives within a person. And I would imagine that that's a central issue in those topics that you're interested in, is dealing with competing interests between people and competing objectives within a person. And so I can't think of any reason why formal modeling wouldn't be a useful tool in that area. Obviously, you'd have to do some work to figure out how to structure the model and to frame and develop those trade-offs. But I think it would be worth trying, I would think.
Yeah, I mean, I'm working on a paper now, and dual objectives function: do the right thing and be profitable, or do the right thing and take a financial cut. And I'm theorizing kind of those different conditions. So it sounds like I'm already informally theorizing these things. So yeah,
right.
Really interesting.
Right. Yeah. And one nice thing about formal modeling is it lets you think of those as a continuum, right? Yeah. Where you can have two objective functions and then aggregate them into an aggregate objective function, which is, what we would call a convex combination of the two, right? So it'd be like fractional as you move from it could be, 100% one, 50% one, 50-50 or 100% the other, or anywhere in between by putting a parameter in there that captures the convex combination of the two objectives. Jeff, what's your interest?
Yes. So I'm also a third-year PhD student. I would say that my interests lie more within ethics and OB. And within those papers, I haven't really seen a lot of this kind of method being used. I've seen a lot of it more in economics and strategy papers. But at this stage in my career, I'm always interested in exposing myself to new kinds of methods. At the very least, like what you talked about with Jung Hoon, at least so I can be a better consumer of some of the papers that I read, but also, I don't know, it might be an opportunity to sort of distinguish myself if this is something that I could make use of, if nobody else is making use of these kinds of methods within the field that I'm interested in. So yeah, so I'm glad to be here. Thank you for putting it all together. I look forward to it.
Yeah, thanks. And so I asked you guys to read that article by Philippe Chazard, and he was really focused particularly on the application, and his work is focused on the application of formal models to organization theory, right? So things like the structure of decision making, who has what decision rights on what decisions, those kinds of things are very central to his research. And so I think it's at least on its way towards moving into the topics that are of interest to you.
Good.
So I think you know, again, people who are interested in those topics can get in early and be one of the pioneers. Amita, how about you? What's your interest?
Hi, so I'm faculty in the management department on the operations management side. Prior to joining Baruch, prior to coming to academia full time, I was a management consultant in the operations world. So what's interesting is my current research, even when I was as a consultant, I was always working with quantitative models for clients. And I always end up with two extremes, either like 100,000 observations of data or very little data. So so working with data in these two extremes, you do end up with limited modeling capabilities in a way. One is you're working with the entire population, so I guess that. The other one is very little data, and I think what really sort of caught my eye was the fact you talked about working with sort of small data sets and how does formal models help you with that. So it's learning a new modeling method. So that's really what drew me.
Nice. Okay, good. I see we have two more people. Is it Xiaolian? Am I pronouncing it right? Oh, we can't hear you.
Yes. Hi.
Hi.
Yeah, I'm Xiaoli.
Xiaoli.
Yes. Hi.
My apologies for the mispronunciation.
I'm a faculty in the strategic management area, and my research has been evolved around corporate strategy, merger acquisition, strategic alliances. I was actually used to be a faculty member at Purdue, so it was. I think I saw you before at the annual reunion at the academy. Sometimes.
Okay.
Yeah.
Yes.
Hi. Yeah. So I'm not very familiar with formal modeling. It's something that I just want to explore and learn. So that's usually I work with archival data. So this is something that I want to learn.
Well, welcome on board. So I asked everyone to take a look at the workshop video on formal modeling and management research from last year's Academy of Management online conference, and to read over two articles. One was Philippe Chazard's, I think it's a Journal of Management article, Certum Quod Factum, How Formal Models Contribute to the Theoretical and Empirical Robustness of Organization Theory. And then the second article was Analytic Models in Strategy, Organizations and Management Research, A Guide for Consumers by Doug Hanna, Ron Tidhar, and Kathy Eisenhardt. So let me just check in. How many folks got a chance to actually read at least one of those articles? Anybody? No, some, okay, a few, 2, 3, okay. So maybe I can just ask those of you who did have a chance to look at those articles, what were the key points that you got out of the article, the article or articles that you looked at?
Well, I would say out of the Philippe, I'm pronouncing his name wrong, but out of the article, How Formal Models Contribute to the Theoretical and Empirical Robustness in Organization Theory, I mean, one, he did talk about just aiming this at PhD students, but one of the biggest takeaway is just using formal modeling just to organize yourself and your thoughts and use it in a way so that you are being strategic in how you're focusing your papers and developing your ideas. And then also just taking you through a process of how to do this efficiently. And then I would say the second paper, I mean, I kind of mentioned before, I thought my biggest takeaway were those two charts that they have in terms of just how you can think about formal modeling and how you can use it. Yes, the research question and looking at how you write your research question. And then there was a nice graph, another table, which is below that, things that gives us some examples. And I thought it was really interesting the way that this was even laid out, even just the structure of how the kind of the headings, what's your research question, your construct, etc., was really helpful in just kind of how you can think through your ideas. And so those are my 2 takeaways.
Great. Okay. Anybody else have some observations from the articles, or something that you learned, something that surprised you that you want to share?
Yeah, I just wanted to share something. As I read through I think it's his name. It's the same one that Nikisha mentioned. Cesar, I guess, is his last name.
Yeah, I think he pronounces it Shazar. I think it's
okay. There were 2 interesting things in that article. One was that he talked about models need to be simple and yet at the same time, lead to some surprise. And at first I was thinking that might be somewhat contradictory, and I come back to the point you made about your conversation about M&As, right? I mean, you've got thousands of articles that have looked at a particular topic. We want models that are simple, but at the same time, we're going to reveal some new, so it's going to predict something new. And does that become more difficult the more, the more papers have looked at a particular phenomenon? So I thought that was one interesting challenge is, how do we come up with simple models that are exploring something new in well-trodden areas? And then the other thing at sort of a more, abstract level, there's been this, I don't know how recent it's been, but a relatively recent conversation around this issue of surprise and novelty. And, it goes back to the famous article about, what is interesting, what makes interesting research. And we all want the aha moment, something that's counterintuitive. But there are others that suggest that, what we should really be doing is looking, not for things necessarily that are counterintuitive, but looking for, mundane is the wrong word, but more predictable, less surprising, and some of this comes with the, replication research and things like that. And so I'm sort of wrestling with, how do we build the right kind of model that's simple, that's surprising, but that's not so surprising that it seems post hoc rationalization.
Right. Yeah, and there is, I think, some literature now arguing that if there's a trade-off between interesting and important, then maybe maybe we've gone too far on the interesting side and neglected the important side, right?
Yeah.
Good. What I'm going to do, I think, is give you a primer on using the Wolfram Mathematica software to do some just very basic economic models. And as a kind of a baseline for you to understand what the various parts of the modeling process are. Obviously, these are very basic models, and so the kind of models I wind up doing are very much more complex than this, but they nevertheless still follow the same basic set of processes that I'll show you. So if you have the Mathematica software installed on your computer, I invite you to start it up and follow along and try these exercises yourself. Okay. Okay, so I just want to first, for those who are, by the way, how many people have the Mathematica software installed and ready to run here? Okay, that looks like about half, no, more than half the group. Okay, so I'm just gonna first point out a few quirks of Mathematica that you need to know. So the first thing I'll point out here is whenever you need to put comments in your Mathematica code, it uses these symbols, the parenthesis followed by the asterisk, and then the asterisk followed by the parenthesis to designate it as a comment that Mathematica should not try to evaluate. It's just a comment, right? And you can do that in the middle of, as a separate cell, right? So basically, the way Mathematica works is that each operation takes place in a different cell. You see over here on the right-hand side that there's a little bracket. I don't know if you can really see that, but there's a little bracket to denote that this is a cell by itself. It tells me that this is the first cell I've been inputting in one. And it will keep track of cells in order. So I could do it. I could do it this way, or I could actually embed comments inside of other Mathematica commands. So, for example, if I wanted to just do a simple plot. And I wanted to embed a comment in the middle of it, I could do that. So I would say quadratic plot, right? And it will know, Mathematica will know not to try to evaluate this as part of the command because it's in these parenthesis asterisk thing, right? And there you go. So I've got my my plot, right? So okay. So I'll point out.
Questions, Richard. Sorry, I'm going to interrupt.
Please, yes, please do. I should have said that. Please do interrupt if you have any questions, comments, or concerns. Yes.
Is Mathematica case sensitive?
Yes, it is. It is.
Okay.
Right.
And how do I execute a command? Is there a shortcut way to execute a command?
Thank you. Yes. I obviously was not thinking of. Okay, so what I do when I execute a command is I hold down the Shift key and press the Enter key. So
Okay.
Shift Enter is what executes a command. Right. So that's something that's so basic. I didn't even think about telling it to you because I'm so involved in this. Right. So I'm too close to it. So if I wanted to, yes, do the opposite. What I'm telling it is to, plot this quadratic function, which is the opposite of the one above, from -4 up to +4. And I just press Shift Enter and boom, there it is. Okay. Mathematica is very powerful. It has a lot of functions. I think one of the things I asked you to do, I don't remember if it's for this session or the next session, was to download the Mathematica book, which is available as a free PDF online. It's about like 1,000 pages long, and it has details about literally hundreds and hundreds of commands. I've been working with Mathematica since the mid-1990s, back when it was version 3. And even in all that time working with Mathematica, I feel like I know maybe about 10 or 15% of what Mathematica can do. Because it just has so many commands and so powerful. So I say that to say, don't get intimidated by the depth of that document. Okay, so I'll point out a few other things here. One is, and this is a quirk, right, of Mathematica. You see here 3 different kinds of parentheses or brackets, right? You see the curly brackets here, the rounded brackets here, and the square brackets here. And those all 3 have very different meanings in Mathematica. Now, I know if you look at a regular mathematics textbook, sometimes these different brackets will be used almost interchangeably, but Mathematica is very picky about which brackets you use. It's within a mathematical expression, use the rounded brackets to indicate the order of operations, right? So what I'm telling it here is I want you to square x first and then multiply it by -1, right? I'm not saying take the negative of x and square it, right? So for example, if I did that, I changed where the brackets are here, this would give me the opposite parabola, right? Okay, so I'm telling it the regular rounded parentheses tell it what order of operations to do. Okay. The square brackets are what you use for a Mathematica function, right? To give a Mathematica function its arguments, right? So that's the word I was looking for. To give it the arguments of a Mathematica function, right? So, for example, if I if I wanted to know the square root of 37, right, I need to use the square brackets here, not the rounded brackets. Okay, now that just tells to me now. So this brings up another point, which is that Mathematica is superior to some other mathematics softwares like MATLAB. MATLAB, in my opinion, doesn't do nearly as much as Mathematica does, because MATLAB is focused on numerical mathematics, whereas Mathematica can do both numerical mathematics and symbolic mathematics. So here I've asked Mathematica to give me the square root of 37, and it's given it to me symbolically, not numerically. If I want the actual numerical value of the square root of 37, then I have to use the n function, which says, give this to me numerically. That's what the n function does. So I've got the square root function inside the n function here, and it will then tell me the numerical value of that. Okay. Okay. And then finally, the last thing was these curly brackets. So braces, sometimes they're called. Braces are used in Mathematica to identify a set. Sometimes Mathematica functions will be functions of a set. So in this case, the plot function is a function of two arguments. It needs the function that you're going to plot, and it needs the range that you want that function plotted over. And that range is identified as a set. The first element of the set is the variable that you're varying within the range. The second element is the lower limit of that variable or the range, and the third element is the upper limit of that variable or range. So but some sometimes we may use sets for other purposes. Sets are also used in Mathematica as a way of representing matrices. And so if you're doing matrix algebra, you're basically doing nested sets within sets. So there's a lot of other applications for sets, but sets are always identified with the curly brackets. So, okay, so I just wanted to go through those little quirks so you understand, what those quirks are. So let me save this. Okay, so each Mathematica file is called a notebook file, and as you can see up here, its file name extension is .nb for notebook. Now, let me just close this, and I'll reopen Mathematica. So one thing I'll mention here is that Mathematica remembers everything that you've done, and that's true even if you open a new window, right? So if I open a new window because I want to do something maybe related but different here, right? Let's say I want to plot 3D. I'll do a 3D plot here of let's see, what did I actually, before I do that, let me just define a variable over here. So let's say y equals sine of x. Okay. So now if I open this new window, I open this new mathematical window, let me actually I'll do a regular two-dimensional plot here just to make it easy, right? It has not forgotten everything I did in the previous window. So if I tell it I want to plot y over the range of x minus 3 to 5, or something like that, right? It will do that for me, right? And you'll notice here that even though this is a new window, it's continuing the numbering from the old window, okay? So I just say this as a warning that if you want to start over completely fresh, you cannot just open a new window. It's not like, you know, Microsoft Word where you open a new document and it's completely new document. If you want to start over fresh, you really need to either completely exit out of Mathematica and restart, or there's a command called clear.
On resetting the variables, what if I redefined y as x squared?
You can do that. You can do that, right? So let's say, right. So let's say I do that here. Let's say I'd say y equals cosine of x now. Okay. Now I can go back up here and rerun this, and it will change the graph. Okay, but I had to go rerun the graph. It wouldn't have done that if I didn't rerun the graph, the plot function. It doesn't automatically update the cell. I have to go through and re-update the cell, right? Or I could do, you know, tangent. And by the way, every time I'm executing a cell, I'm doing it by Shift Enter, right? So what I'm going to do, for the sake of being able to start with a clean slate, is I'm going to exit out of Mathematica completely. And apologies for the delay, because Mathematica does take about 30 seconds to get started, maybe 10 seconds, maybe I'm exaggerating a little bit. Okay, so now that you understand a little bit about the quirks of Mathematica, let's do the simplest, you know, basic economic model. Now, of course, as I mentioned earlier, you know, formal modeling can be applied much more broadly than just economics. It's just that, you know, that's the type of modeling I'm most familiar with, and so it's going to be easiest for me to illustrate. You know, but to Jared's point, it you know, it can be used for other purposes, you know, organizational purposes rather than economic purposes. But I'm just more familiar with the economic model, so I'm just going to use them as my basic examples. Let's do the optimum output choice of a monopolist. Okay, it doesn't get much simpler than that in economics. Okay, so there's a sequence of steps I'm going to go through that are kind of the practices I've developed over the years for doing this sort of thing. The first step is I'm going to define and define parameters of the model and assumptions about them. So I'm going to create a set called parameter assumptions. By the way, you may notice that every time I define an object for Mathematica, I always start it with a lowercase letter. And the reason for that is that all Mathematica's built-in objects and functions always begin with an uppercase letter. So starting my objects with a lowercase letter means that I will never by mistake crash into one of the existing Mathematica objects, right? I won't you know, mistakenly try to define a variable that Mathematica already has, that is already using that symbol for. So I always start with a lowercase letter. Okay, so.
Sorry, may I ask you?
Yes.
An object in Mathematica is what? I didn't hear that.
Yeah, so I guess what I mean is any function like we were just looking at sine or cosine or any built-in variable of Mathematica like pi, right? So pi is a built-in variable in Mathematica,
Okay.
right? Now, if I wanted to know, the numerical value of pi, I could do this, right? Now, and so I would get myself into trouble if I tried to use that as a variable name, capital P, lowercase I. However, I could use lowercase p I, right? I could say pi equals q times m, okay? Right, and so that doesn't give me trouble, right? But if I try to do, because economists often use pi as a symbol for profit, right? That's the variable that they use for profit often. But I don't want to get Mathematica confused to think that I'm really talking about 3.14159. I'm talking about just a variable pi, right? Right now, if I try to execute that same command with capital letter pi, right? It's going to give me an error code for this, right? Symbol pi is protected, right? So I avoid that sort of thing by always, when I'm defining a variable, always using a lowercase letter to start it. Are we good, Maria? Yep.
Yes, thank you.
Okay.
Thank you.
Okay, good. Okay, so let me bring this parameter assumptions thing up above my definition of pi. And I'm going to delete out these other cells. So if I want to get rid of a cell, I should mention, I just grab it here on the right and press the delete button, delete key. Delete that. Okay. So for my parameter assumptions, I'm going to define a set of assumptions. And by the way, when you're defining a variable or a set or whatever, you can use multiple lines. You can overflow, you don't have to stick with one line, and that's helpful for keeping your code readable. So I'm going to start by opening the set with open brace here, and I'm going to close it over here. Okay. So, and this lets me spread things out so to keep it readable. So first I'm going to tell it that my parameters are all real numbers, because Mathematica by default assumes that numbers are complex. And so if I have a complex polynomial function that I'm later trying to solve for, it will give me, I should say a complicated polynomial function. It may give me solutions that are complex solutions unless I tell it that basically these variables are real variables, not complex variables. So I'm going to tell it that I'm going to define three parameters here, A, B, and C. And I really do not know why Mathematica requires me to use the vertical bar symbol to separate these variables when pretty much everywhere else Mathematica uses commas, but for some reason in this function it uses a vertical bar. But so I'm going to tell it that those are members of the set of real numbers. Okay. Then I'm going to put a comma in here because I'm going to tell it a few other things about those variables. I'm going to tell it that A is positive, that B is positive, that C is positive, and that A is greater than C. Okay, so there's my parameter assumptions for this very simple model where I'm deriving the optimal output choice of a monopolist. Okay, and you can see here it's giving me this set. In this case, it's not a set of variables or a set of numbers, it's a set of relationships. It's telling me that A, B, and C are members of the set of real numbers and that, these inequalities apply. Now, why am I doing this? Because one of the most powerful functions of Mathematica is the simplify function. which allows you to take really complicated mathematical expressions and simplify them dramatically. But the way that it works best is if you can tell Mathematica the assumptions to apply for that simplification. It will be able to simplify it usually more completely if you tell it the assumptions that you want it to simplify with respect to. So for example, let's say I want to simplify the expression A minus C plus B is greater than 0. Okay, now if I don't tell it any assumptions, it's just going to give that right back to me, right? But if I tell it, simplify that expression with respect to these assumptions, it's going to tell me it's true. So in effect, the simplify function can prove theorems for me. It's really powerful in that regard. Okay, so now let me just explain what each of these variables are. By the way, I'm going to over comment my code. This has become a helpful practice for me because just by way of experience, often what will happen was I learned this the hard way. I would develop a model in Mathematica. I would use it as the basis for a paper, write up the paper, submit the paper, and then 3 or 4 months later, I get reviews back on the paper. The reviewers say, hey, this is pretty okay, but we really want you to make these changes to your model. And then not having looked at the Mathematica file for 3 or 4 months, I then open my Mathematica file and it's like, what the heck was I doing? I cannot remember what these variables mean, why I used them, et cetera, et cetera. So I've tried, I don't always do this perfectly, but I tried to get into the habit of adding as many comments as I can think of as a reminder to myself later of what the heck I was thinking. So I'll tell it that, make a note to myself, parameter A equals the intercept of the inverse demand function. I'm going to put a comma in here so I can keep these lined up. If I don't put a comma in here, it's not going to line these up correctly. You see, it's going to, for whatever reason, it shifts that B over a little bit to the right.
I was going to ask that because I'm typing it as well and typing the comments and it kept shifting.
Yeah,
things.
I don't know why Mathematica does that. I wish it wouldn't do that. But here, I'm just going to type B equals negative slope of inverse demand function, right? So now if I go back up here and I put a comma in, boom, it lets me line these up properly then. Otherwise, it won't let me line them. I don't know. Don't ask me about that. This is just another quirk of Mathematica. And then I'll say, oops, I didn't do that. There we go.
Can I ask a more basic question?
Yes.
Why do you prefer Mathematica over others?
It's so powerful. It can do anything I need it to do, basically. As I mentioned earlier, for example, I guess the closest competitor is MATLAB. And MATLAB just really doesn't do symbolic mathematics well. So for example, let's see, let me get my old friend function y up here, right? Sine of x times tangent of x times x squared. Okay, I have no idea what that looks like. It's probably very ugly. Just do a quick plot of that. Oops. Okay, so there's this very ugly function, fine. But let's say it's not that function that I'm concerned about. Let's say it's the derivative of that function, right? So if I want to take the derivative of y, all I do is say, I'm going to define that as dy. So now it's going to take this, the D symbol here is Mathematica's built-in derivative function. So it's going to take the derivative of y with respect to x. Right? There it is. Right? So, you know, that's pretty powerful that it can instantaneously give me that that solution. Right? Now, here's something that's even more impressive to me is that it can go backwards too, right? So integration is often pretty darn hard, right? Especially if you take a look at a function that's as complicated as this. If I handed that to, you know, even a, you know, second-year calculus student and said, integrate that with respect to x, it might take them a couple of minutes, right? But I can tell Mathematica, integrate dy. There we go. So yeah, so I'm kind of impressed that Mathematica can do this sort of thing, right? This is, you know, that it can take this function, plot it like instantly, take the derivative instantly, and then integrate and get me right back to where I started from. I mean, that's pretty powerful. So Elena, does that kind of answer your question about why I like Mathematica?
Yes, it does. It was primarily, especially the part where you kind of compared it to MATLAB, and yeah, I can see the power in this. It's just, it seems a little bit more quirky than MATLAB, and that's why I was wondering why you preferred this one. But
right, undoubtedly it is more quirky, but it kind of has to be more quirky because it's doing more things.
Yeah, and it seems like the quirks, putting up with the benefits of it outweigh the quirks of it.
Yeah, I think so. I'm sorry, somebody else had a question?
I was just going to ask you, have you ever used the plugin to Python? I saw that it has a Python plugin that you can...
I was not even aware that that existed.
Yeah. So yeah, so I think, and it might have a Stata one too. So I'm wondering if you...
Yeah, I have not done either of those. So I mean, this again is testimony to how powerful Mathematica is and how much it can do, is that, you know, again, even after 20, 25 years of working with Mathematica, I still barely scratch the surface in terms of its capabilities. Okay, so just again, defining the parameters, I'm going to define A as the intercept of the inverse demand function, B as the negative slope of the inverse demand function, and then C as constant marginal cost per unit.
I don't know when is the right time to ask this question, but may I ask you something quickly?
Of course, yes, please just jump in anytime you have a question.
So I was wondering in Stata, for example, if you don't know how to code something, you can always write into the help function, and then a menu pops up and it describes you how the function should look like and whatnot, and gives you examples. Is there something like that as well? Because, for example, I wouldn't know that, I don't know, you only write a D for derivative or something like this, like these right. Things that you already do naturally. Is there an easy way without going to the 1,000-page manual?
Absolutely.
Is there something integrated, yes, or a community, or there's also a big Stata community where you just write a question and they show you even how the whole thing would look like, and you just plug in your variables, let's say. Fine. I know it's an easy workaround, but I'm just wondering if for learning it faster, is there something like that around?
There is. Wolfram does have a vast online community to support Wolfram Mathematica, but 99% of the time, the answers that I need, I can get directly here from this Wolfram documentation window. So I just click on Help, Wolfram Documentation, and then it brings me a window like this. And let's say I was wanting to, let me widen this out so it can, okay. Let's say I want to, you know, learn about visualization and graphics, right? So I could go here and let's say I want to learn about geographic visualization, right? Then it's going to give me a list of all the commands that it can do with respect to geographic visualization, none of which I've ever used, you know, in my 25 years, but I can imagine that if I had geographic data, this would be very helpful for me. And then I can click on each of these and it can tell me, you know, basically how to use this function. What are the arguments of the function? I can click on details and options and it'll tell me all the different options I can put into this function. And it'll show me some nice examples. So, and you know, it'll tell me, you know, what I can and can't do with this thing. It'll show me options to consider, and it'll even show me some neat applications of the
Okay, so these are real code examples actually.
yes,
And then show, and so it shows the code and the output basically.
exactly. And I can just, if I needed to, I can, just like any other cell, I can grab this cell and copy it. And
Okay.
you know, or I can grab parts of it and copy it and paste it into my code.
Okay, cool. Thank you.
Yes. So or you know, like let's say I don't even know how to take a derivative, right? So I can go up here to the search window, the search box, and say derivative. And it will show me all the symbols that have to do with derivatives. And I can click on any one of them. So the one I've been using is the partial derivative, D, or if I needed to use the total derivative, I could go dt. And again, it would give me all those details, you know, options, examples, relationships to other related commands. And in fact, there's tutorials here I could go into. I think all of this stuff that's in the Wolfram documentation window appears in that Mathematica book somewhere, but it's just easier to access this way because you can search it. Let me see what would have happened if I did this integrate without the assumptions. Yeah, it got there even without the assumptions. Okay, so I've defined my parameters. And by the way, you know, in my papers, I prefer to use Roman letters like, you know, A, B, C, X, Y, Z for endogenous variables that are, you know, derived within the model. And I generally prefer to use Greek letters for parameters that are exogenous, that are determined outside the model. Just for simplicity, I've done it with A, B, and C rather than alpha, beta, gamma. But if I wanted to, the way that you get those Greek letters is you first press the escape key, and that brings up that little triple dot symbol. And then I could type a letter like G for gamma, and it's going to give me a list of symbols that begin with G. So I would pick gamma here. Or if I wanted alpha, I type the escape key and then A, and it'll give me a set of symbols that I could use. And there's a lot of them that begin with A, but I would just pick alpha, right? But for simplicity, I'm just going to use A, B, and C here. I'm going to then define so in this case, because I'm dealing with a monopolist, there is only one objective function. If I were dealing with a duopoly, there would be two objective functions, or an oligopoly. There might be multiple objective functions, 3, 4, or 5. But here, I'm only going to have one objective function, and I'm going to, as I often do, build it up in pieces, so I can start with the simplest assumptions. First, define the inverse demand function. So a demand function would give me quantity as a function of price. But what I really, for simplicity's sake, want to do is get an inverse demand function, which would give me price as a function of quantity. Price as a function of quantity. So P equals A minus B times Q. Okay, so that's going to be my inverse demand function, giving me price as a function of quantity. Next, define margins, the firm's margin. So I'm going to call that M. And margin is basically just going to be price minus cost. Okay. Now, you remember here, I defined pi or profit as Q times M, and it just simply gave me MQ before, right? Because I hadn't defined M yet. Now I just defined M, so if I now ask it, hey, what's pi? It's not going to tell me M times Q anymore. It's going to substitute this in for M, right? So, and I would do the same thing here if I reran this cell. Okay, so now I have, built up my.
Richard,
yes, please.
if I may interrupt you. Did we define Q?
No, because Q is going to be an endogenous variable.
Okay.
Right, because I'm going to be choosing Q. My monopolist is going to be choosing the optimal output.
Mm-hmm.
So it's not a parameter.
Okay.
So yeah, so I haven't.
Outcome variable, right?
Right,
like
it's my
trying to predict.
Right, exactly. So next, define profit function. Okay, good. Okay, so now I've got all my comments in here telling me every step I took along the way to create my objective function. I got the inverse demand, subtracted out cost to get margin, and then multiplied margin by output to get profit. Okay, so the next step, so let me number these steps, because all of my models, everything I do follows the same pattern, right? So step one is define the parameters of the model and my assumptions about them. And I can, I think, delete out all this illustration of why I love Mathematica. And by the way, you can see I'm grabbing a whole bunch of cells on the right by, I went first to the top cell, selected it, scrolled down to the bottom cell that I wanted to delete, hold down the shift key and select that cell, and it's going to select everything in between. And I press delete and it's gone. So that was the first part, define the parameters of the model. The second part is define the objective function. Okay. The third part I'm going to do here is derive the first and second order conditions. Okay. Just to clarify what I mean by first and second order conditions. Let me get my x squared plot up here again. Actually, let me do minus x squared from x is minus, oops, case sensitive, x minus 2 to 2. Right. So if I were trying to, so what we're going to be doing is we're going to be maximizing the profit function, right? Because that's what a monopolist would want to do. They would want to earn the maximum profit. So let's say I was trying to maximize this function, right? I would want to find this point here at the top of the hill. And so how would I do that? Well, I would take the derivative and look for the point where that derivative hits 0, right? So that the derivative of this would be the first order condition. It would be the point where that derivative, which then would be minus 2x equals 0, right? Because minus 2x is going to be the derivative of that. D minus x squared with respect to x, it's minus 2x, right? So my first order condition here would be minus 2x equals 0. So I'd be looking to solve the equation minus 2x equals 0, which would be x equals 0, right? Now, that gets me to a critical point, right? That's all it tells me, is that x is a critical point in this function, right? It doesn't tell me whether it's a maximum, a minimum, or a saddle point, right? So in this case, what I've drawn here, it's a maximum. But if I took the minus sign out here, it would be a minimum, and I would get the same critical point because, 2x equals 0 has the same solution as minus 2x equals 0, right? So my solution to my first order condition of x equals 0 doesn't tell me if it's a minimum or a maximum, right? It could be either one. In fact, if I make this x to the third, right, instead of x squared, and I look for the derivative of that, the first order condition of this would be 3x squared. So 3x squared equals 0 would be my first order condition. That would also be x equals 0. And as you can see, this is neither even though it's a critical point, it's neither a minimum nor a maximum. It's a saddle point, right? Saddle point means it's a minimum if you move in one direction. In fact, move to the right, it's a minimum. It's a maximum if you move in another direction. Move to the left and it's a maximum, right? So the first order condition is not sufficient to tell me whether it's a maximum. It just tells me it's a critical point. Could be a minimum, could be a maximum, could be a saddle point, right? So that's why I always need to check the second order conditions as well. The second order condition is what tells me whether it's a minimum or maximum. Actually, let me get that example back up again. So y plus equals, let's say x squared, right? Y minus equals minus y plus, okay, and y, actually, y cubed equals y plus times x. Okay, fine. So that's going to be x cubed, right? Okay, so to know whether those are minimum points or maximum points, remember this y plus, it would be a minimum, right? Because if I go plot right, that shows me that this is a minimum if I graph it. But mathematically, the way I know that it's a minimum is, first, let me take the first order condition. And what I'm going to do here is I'm going to define this not just as a derivative, but I'm going to set the derivative equal to 0. Now, here's another Mathematica quirk. The ordinary equal sign here that I've been using to define variables simply means, it just means I'm assigning this symbol to on the left of the equal sign to be the expression that's on the right. This is just an assignment operator. It's not an equal sign in the sense of an equation. So if I wanted to find an equation, I need to use a double equal sign, right? So 0. So this is going to be an equation, right? And you can see that now the symbol y plus FOC is the symbol that represents this entire equation, right? So now if I want to know where the critical point is, I can solve that equation. And it tells me the solution is x would be where x is 0, right? Now, if I do that same thing for these others, it's going to give me the same solution. Let me actually copy all of these things. 1, 2, 3, 4, copy, paste, and now I'm just going to do a quick search and replace here. I'm going to replace y plus with y minus. Next, replace, 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 replace. Okay, good. So now, again, you can see here now, this tells me that by plotting it, I can see that the critical point is a maximum. I define my first order condition here. Right. And that I solve that. And it gives me the same solution. So it tells me that the critical point is in the same place as for the other function, right? And now the same thing here. Okay, now let me do a quick replacement.
Sorry, also that all my silly questions are now recorded, but why did we do exactly this step now? Sorry.
Okay, so what I'm trying to illustrate here is why I need to do both the first order condition and the second order condition, right?
Oh, okay, okay.
Because the first order condition tells me where a critical point is, but it doesn't tell me whether it's a maximum, a minimum, or a saddle point, right? So I'm illustrating that these three functions, y plus, y minus, and y cube, all have the same critical point at x equals 0, but in one case it's a minimum, in one case it's a maximum, and in the last case it's a saddle point, right? So okay,
so this was for the second one, right?
Right. So the second one is giving me the
Okay.
same critical point, x equals 0, right?
Okay.
That it
Okay.
gave me back here with this other function, right? So
Okay.
same critical point. But I don't know, unless I graph it, which one is a maximum, which one is a minimum, right? But I'll show you in a moment how I can know that arithmetically by using the second order conditions, right? So let me repeat this for this y cube plus, I'm going to substitute y cubed for y plus, y next, replace, 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 replace. So now, again, plot y cube, it gives me this, okay, it gives me this, this cubic function. If I take the derivative of that to get the first order condition, right, and set it equal to 0. If I take the derivative and set it equal to 0, it gives me the first order condition, right? And then I solve that. And once again, it gives me the same solution. Now, I should point out a few things here about what the solve function gives me, right? So you'll notice this is a set that is a set of sets. So why is it a set of sets? First, it's a set of replacement rules, right? This is telling me that if I want to find the solution to this first order condition, that I have to replace x with 0, right? Now, why does it need to give me that as a set? Well, because in this case, I'm just asking it for the solution to a single equation. I could use the same solve function to get the solution for a system of equations, 3, 4, 5, 10 equations, right? And if I have a system of 5 equations and 5 variables, the solutions it's going to give me are 5 replacement operators, right? So it would be like x1 is replaced by 0, x2 is replaced by 7, x3 is replaced by 9, whatever. And it would need to give me those as a set of replacement operators. So it would, it would give me that as a set. So here it's kind of a degenerate set because it only has one member, right? There's only one variable I'm solving for, although in a system of equations, there could be many variables that I'm solving for. So that explains why, why we have this set, this inner set. Why do we have the outer set? Well, we need the outer set symbol because, this happens to be a linear equation. So there's only one solution to a linear equation. But if this were a quadratic equation, then there would be 2 solutions. If it were a cubic equation, then there could be 3 solutions, etc. And so when I tell it to solve, it would need to give me all of the solutions, right? So I'll just give you a simple example of this. So I can, here was everybody's bane in high school was the quadratic equation. A times x times x plus b times x plus c equals 0. I want to solve that for x, right? So you can see that it gives me two solutions, right? This is the quadratic formula, which has two solutions, right? Minus b plus or minus the square root of b squared minus 4ac over 2a. So it's that plus or minus thing that's giving me the two solutions, right? So that's why it's a set of sets, right? Because within each solution is a set of replacement operators, and there can be multiple solutions. So it's a set of sets. Okay, so that's what's happening down here. Is it's giving me a set of sets for the cube solution. They both happen to be the same solution.
So I guess well, is there a way where you can just see the commands without the output?
Yes.
That's a good question. Yeah.
Good point. Okay, so here.
I think that might be easier for us to see if we could just hide the output, just to see the code that you've used to set this up.
So thank you for asking. So let me take some of these and I'll just paste them in down here and you can see. Okay, so if I end the command with a semicolon, that tells it don't show me the output. Right.
So that just runs it. It doesn't show you the output.
It just runs it. It doesn't show me the output.
So you still do the shift enter, the shift return.
Yes.
Okay.
Yes. Now I was going to show you about second order conditions, right? So we've got these three cases, x squared, minus x squared, and x cubed. They all have the same critical point, but I need to know which one is a minimum, which one is a maximum, which one is a saddle point. I get that from the second order conditions. So, okay, so let me define the second order conditions here. Y plus SOC. Now I'm going to, I'll show you two ways I could do this. Okay, so I have this derivative. This was the first order condition. I could just simply put another derivative operator around this to take the second derivative, right? So I already took the first derivative, and this would give me the second derivative, right? Or I could just simply grab this first order condition, but the thing is I cannot take the derivative of an equation. What I need to do is just take the derivative of the left-hand side of the equation, right? So the way Mathematica handles expressions like this is everything is kind of a set in Mathematica, right? So I can ask it, okay, what kind of expression is this? Okay, so I can ask it, what kind of expression is this? Well, it's going to tell me it's an equation, right? And I can ask it, okay, well, how many parts are there to that equation? And it's going to tell me 2, because there's a left-hand side of the equation and a right-hand side of the equation. Now, if all I need is just one part of this equation, like the left-hand side, I can just tell it I want just part 1 of the equation. Now, here again is another Mathematica quirk about the brackets. When I use double square brackets, that tells Mathematica I want to extract a part of an expression, right? And there it goes. It pulls the first part of the equation, which is the left-hand side of the equation. It pulls the 2x, right? If I wanted to...
question.
Yes.
Do you need to do all these 3 steps? So do you need to first identify the length and all that, or can you just go straight?
No, obviously I'm just showing this for you for.
No, I appreciate it, but I was wondering if, there's some commands that you have.
No,
to
I mean,
do.
obviously I know that this is an equation and it's got 2 parts, right? So I could just skip directly to telling it, asking it, what, give me part 1. Right. So again, if I went back to A greater than B greater than C, sorry, I apologize for confusing you. I should use it's head and length. I don't know why I said parts. Yes, sorry, head and length. Okay, so if I want to get the middle part of Z, I can just say, give me part 2, right? And that's B. Or give me part 3, and that's C, right? So it can give me the parts from the start, numbering up from the start, or it can give me the parts numbering down from the end. So if I only want the last part of Z, I can tell -1, and it's going to give me the same result. It's going to give me C. Or if I want it to give me, -2, it'll give me B. Or -3, it'll give me A. So I can number the parts from the beginning as positive numbers or from the end as negative numbers. Anyway, so I mention all this because I wanted to show you the simpler way to derive the second order condition, right? Which was instead of, doing a derivative of a derivative, I could just simply do a derivative of the first order condition of part 1 of the first order condition, right? So I can replace this whole expression here with FOC part 1, and it gives me the same result. Okay, so what happens if I take this down to the other 2 examples, right? Okay. Okay, so now it's going to show me -2, right? So up there, when I was doing y plus, it showed me that the second order condition was 2. So actually, this is not really a condition. What I need to say is, to make this a condition, I need to make this a inequality, right? So the second order condition for a maximum is that the second derivative is negative. The second order condition for a minimum is that the second derivative is positive, right? But since what we're doing here is we're looking for a maximum, we're doing profit maximization. In some cases, you might be doing cost minimization or something like that. So you'd be doing the reverse. But in this case, since I'm doing profit maximization, I am looking for a negative second derivative. So I'm going to define the second order condition as the second derivative is negative. And it's going to tell me that that's false, right? So I know that this cannot be a maximum. I know that by looking at the graph too and seeing that it's really a minimum. But if I don't have, if I'm dealing with a very complex function, complicated function where it's impractical for me to plot it, then I need to use these second order conditions to tell me if it's a maximum or a minimum or a saddle point, right? So let me copy this. Actually, you know what? I'm just going to do this. So now if I ask it, is the second derivative negative, which is what I want for a maximum, it's going to tell me true, right? Okay, so let me do this also for the cubic one. Let me get rid of the less than operator for a moment. This is telling me that the second order condition here is not just a constant as it was above, right? Above it was +2 or -2. Here it's a function of x, right? So if I know I want this to be negative in order for this to be a maximum, that's my second order condition, but I need to evaluate the second order condition at the first order condition, at the solution. So let me actually call this, I should have done this earlier. I'll call it y cube FOC solve, right? Okay. So in order for me to know, is this solution a maximum or a minimum, I need to substitute this solution into the second order condition. Okay. So I'm going to say, replace all y cube SOC, and I'm going to replace it using this replacement rule, but I have two replacement rules here, so I just have to pick one of them. I'll pick the first one because they're both the same, right? And it's going to tell me false, right? Because what it's done is it's taken the x equal x replaced by 0 here in this first replacement rule, substituted that in here, and that got 0, and 0 is not less than 0. So it gives me false back. So this is a saddle point because the second derivative evaluated at that solution, at that critical point, is 0, right? So if I take this and I just simply grab this piece without the inequality, right, it's going to tell me that let me just spread this out a little bit to make it a little bit easier for you to read, right? I'm replacing the second derivative with the value x equals 0, right? And it's giving me 0 because 6x when x is 0 is 0, right? So anyway, so I say all this to explain why I need to check both the first and second order conditions. The first order condition tells me where the critical points are. The second order condition tells me whether those critical points are a maximum, a minimum, or a saddle point. Okay. Let me get back to my monopolist who I've left hanging for a while. Okay. So I'm going to push all this stuff down. And now my monopolist first order condition is going to be derivative of pi with respect to q equals 0. Okay. And my monopolist second order condition will be derivative of the first part of the first order condition with respect to q is less than 0. Okay. So let me solve that. First of all, let me check to see if the second order condition, well, actually, let me solve the first order condition first. Okay. First order condition solve equals solve that equation for q. Okay, that gives me the solution. Now, because there's only one solution here, I only want the replacement rule. So let me just say, I only want that one replacement rule. I'm just going to pull the first part of it, right? Which is just going to be the set rather than the set of sets. Okay, so now I want to check to see if the second order condition is satisfied. Ordinarily, you would expect the second order condition would be a function of q, so I would need to substitute in this value of q to check whether the second order condition is negative. But this second order condition, because this problem is so simple, is not a function of q, so we can just directly check to see whether it's negative. So what I would do is I would say simplify second order condition with respect to my parameter assumptions, right? Because if I just told it simplify SOC, it's not going to do anything with that. Well, yeah, okay, it gets rid of the -2. But if I add my parameter assumptions in here, it's going to tell me true. Okay, so now what I need to do is, having solved for the optimum output, what I need to do is substitute the optimum back into the objective function. Okay. So this is, what was that? What was I saying? That's 3. So this is 4. Okay. So I'm going to say pi. I'm going to call this the equilibrium pi. So I'm going to replace the q's in the pi with this optimal q. Okay, now that's messy. At least it looks messy. It's not really messy, right? Because I've just simply done a replacement. So what I need to do to make this look a little nicer is I tell it simplify with respect to my parameter assumptions. And boom, right? Lot prettier. A minus c squared over 4b. Okay, so great. So now I know what the monopolist's profit is when they're choosing the optimum output, right? But what I really want to know is, in general, I want to be able to make predictions. I want to be able to develop propositions. So in order to do that, I need to do what we call comparative statics. So use comparative statics derivatives to develop my propositions.
May I ask a quick question?
Of course.
And so all these steps or the recipe you follow, let's assume it's not the context of a monopolist, it's anything
Right.
like it's ethics or whatever, or all these topics that we heard before from the participants. So
Exactly.
would these be motivated by theory, like these are the steps I have to take, or this is this logic I follow because of prior work, or would it be motivated through the context that I'm looking at, perhaps if I want to supplement a data analysis because the context is like that, or is it a mix of both, or what works in your experience?
Yeah, so I mean, I generally all the models that I use follow the same sequence of 5 steps. This is just a very simple version of it. I guess, there might be other kinds of models where you follow a somewhat different sequence. But generally, this is what we're going for. Our end goal is to have propositions about how these 3 parameters affect profit, right? I should have stated that from the start. My goal here is to, let me go all the way back to the beginning. My goal here, let me put it in here. The goal is to have propositions about how changes in these 3 parameters affect the profit of a monopolist who chooses the optimum output, right? So in general, my goal is to develop propositions about how changes in some underlying parameters affect some endogenous output variable. It could be profit, it could be something else, right? It could be market share, it could be a lot of different things. but I want to have some propositions about, at the end of the day, about how the underlying parameters in the model affect an output variable that is an equilibrium, I should say the equilibrium, some equilibrium, some output function in equilibrium, right? So my goal is to develop propositions about how changes in the underlying parameters of the model affect some output variable in equilibrium, right? So if that's my goal, then really I pretty much have to go through the sequence of 5 steps.
Mm-hmm. And you would basically come to this goal because you motivated it in a paper. I'm thinking about now how to publish this. You
Right.
would motivate this in the theory part, that this is an important question to look at, and these are the right variables to look at from theory.
Exactly. Yep.
Okay.
Exactly. So for this simple case, let me take the derivative. So I have the equilibrium profit function here. And that's fortunate. Now, in some of my models, they get so complicated that I cannot directly calculate the equilibrium profit function. Sometimes I have to do an approximation to the equilibrium profit function. Sometimes I may be able to derive properties of the equilibrium profit function without actually knowing the function itself, because the function itself may be too complicated. But for this simple example, fortunately, we know what the equilibrium profit function is. So let me take the derivative of pi with respect to a. Okay. Okay. So that tells me the derivative. Now, what I really want to know is that positive or negative? Does increasing a, remember a is the intercept of my inverse demand function. Does increasing the intercept of the inverse demand function, how does that affect the profit of the monopolist in equilibrium? So what I want to do here is I want to do a little simplify on this, prove a theorem that this is in fact positive. And it's true, right? Because we assumed back in the parameter assumptions that B was positive and that A was greater than C, right? So Mathematica is able to take those rules from the parameter assumptions vector and apply it to this inequality. And that's what the simplify function does, right? So it's proven to me that increasing A increases the profit of the monopolist. Now, if I do the same thing with respect to parameter C, I would expect the opposite, because again, C is the marginal cost that the monopolist pays, and when you increase the monopolist's cost, that should actually hurt the monopolist's profit, right? So let's check to see if that's true. Yes, it's true. Okay. And then I can also check the same thing with respect to parameter B. Although this one will be a little bit more complicated because B is in the denominator here. And I think this is negative. Yes, okay. So that tells me those are the main effects, right? So let me label this as the main effects. Now, if you know my work at all, you know I'm never satisfied with main effects. I'm very much more interested in interaction effects, right? So let's go for some interaction effects. So now I want to get the interaction effect of A and B on profit, right? So I take the the derivative with respect to A, the derivative of profit with respect to A, and I also take the derivative of that with respect to B. I differentiate with respect to B, right? So then it gives me that. And let me check the sign of that. Right. And so that tells me I have a negative interaction effect. Right. Now, if I did this also with the pairing of C and B, I think I would get the opposite. I think I would get something positive, but let me check. C, 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 greater than, yes. Okay. So we have, for this very simple model, we've gone through the 5 basic steps. We have articulated our assumptions and our parameters and our assumptions about those parameters. We have derived the objective function. We have solved for the optimization. We've optimized that objective function to get the equilibrium. And we've checked to make sure that it's a maximum. And then we substituted that back into that's optimal solution back into the objective function. We substituted the equilibrium. I call this an equilibrium solution back into the objective function. And then we differentiated that equilibrium profit function to get comparative statics, right? So those are the 5 basic steps. Using Mathematica, the basic steps for doing a formal model, in this case, just the simplest model, which is a monopolist choosing the optimal output. I can show you a 2-agent model. I'll do the Cournot equilibrium, and you'll see it's basically the same set of 5 steps, except that both agents have their own objective functions, and the equilibrium is not just the solution of a single equation in a single variable, but it'll be the solution of 2 equations in 2 variables, 2 output levels. So I'm going to save this one as Monopoly. Okay. Now, by the way, I'll just show you one other little trick here, which is that when I have saved a file and I want to come back to work on it again, I don't have to keep pressing Shift Enter, Shift Enter, Shift Enter on every single cell. I can just tell Mathematica to execute the entire workbook. So I go up here to the evaluation cell and I tell it evaluate notebook, and boom, it goes through and fairly quickly evaluates the whole thing without me having to press Shift Enter on each cell. Now let me start over. Let me relabel this. I'm going to do a Cournot duopoly. Augustin Cournot was a famous French economist from, I think, the 17th century. I'm going to basically use the same model parameters here. Now, you know what? I'm going to make a little bit of a difference here. I'm going to give one firm a competitive advantage over the other firm. We're going to have that'll give it more of a strategy flavor. CA and CD, right? So A will stand for the advantaged firm and D will stand for the disadvantaged firm. And the disadvantaged firm will have higher costs, higher marginal costs than the advantaged firm. So CA is greater than 0. CD is greater than 0. So I'm going to assume that the disadvantaged firm has higher costs than the advantaged firm, right? And that A is greater than both costs. A is the, again, the the intercept of my inverse demand function. So now I'm just going to say CA equals constant marginal cost for advantaged firm A, and CD is constant marginal cost per unit for disadvantaged firm. Okay, good. Now I'm going to have to change this from objective function to objective functions. Right? We are going to use the same inverse demand function. Nothing changes about that. But there are now going to be two margins. MA for the advantaged firm and MD for the disadvantaged firm. Okay. Now I'm going to define two profit functions. Pi A for the advantaged firm and pi D for the disadvantaged firm. Okay. Now I have to deal with two separate sets of first and second order conditions. FOC A for firm A for the advantaged firm. I made a mistake. Let me back up here. I'm going to say Q. Now we have to have two Qs, right? Because each firm has its own output, right? This or regular Q is going to be the total output for the industry, both firms. So I'm going to define Q as equal to QA plus QD, right? So the total output of the industry is firm A's output at plus firm D's output. So now if I get the ask it for the inverse demand function, it's going to be a little bit more complicated because it's substitute QA and QA plus QD in for Q. And now the margins have to change too, right? So I've got to rerun that because it's not just Q I'm concerned about, it's QA and QD. Okay. And so I made a mistake here in the profit function. I need to specify that it's QA for profit for firm A and QD for firm D. So now my profit function for firm A is that. My profit function for firm D is that. Okay. Now I have to go and derive the first order conditions and second order conditions. So this is where I left off a moment ago. So I've got to take the derivative of the profit of function of firm A with respect to firm A's output. That'll be my FOCA. Okay. I can simplify this a little bit because you can see here that there's a minus BQA here and a minus BQA here. So if I simplify this, it'll just make it a little bit easier to read. Okay, combine the two minus BQAs into one. Okay, so now let me do this again for firm D. Okay. And now what I'm going to do is, let's say, let me just define FOC as being equal to the set of those two FOCs. first order condition set is, right? So now this FOC is a system of two equations. Okay, here's the first equation, and here's the second equation, right? So the only change I need to make here to the solution is I need to tell it I'm looking for two outputs, not just one, QA, comma, QD, right? And as you can see, now it's given me, it's still only one solution, but each solution has two parts because there's two variables and two equations, right? So it's giving me the solution for QA and the solution for QD. Fortunately, because both equations are linear, there's only one solution. So it's a set of sets, but it's a set consisting of only one set because there's only one solution. Okay. So as we did before, I'm going to just get rid of that outer set of brackets by plucking out part one. Now, the second order conditions are a little more complicated here because I have two second order conditions. So FOCA, SOCA, FOCA, QA. Turns out to be the same second order condition as we had before. But we also have a second order condition for firm D. D, which also is the same. Okay, so let me just tell it, I want to know if both second order conditions are satisfied here, right? Because now I have two second order conditions. I need to be concerned to make sure that they are both satisfied. So the double ampersand is the symbol for and, for a logical and. And it turns out to be true. Okay, and as we did before, we want to substitute the equilibrium solution back into the objective functions, in this case, the two profit functions, right? So I'm going to say pi A equilibrium, pi A, and pi D equilibrium, pi D. Okay. So you can see the difference between those two equilibrium profit functions is just that, you know, for firm A, having higher costs hurts firm A, but firm D's costs, if firm D has higher costs, that helps firm A. And then it's the reverse for firm D, right? Firm D is helped when firm A's costs go up and hurt when its own costs go up, right? Okay, so then now we're already down to part 5, the comparative statics, right? And so the two firms are symmetric. Well, let me see. Okay, so that's the derivative with respect to the intercept parameter A. That should still have a positive effect, and in fact it does. Now we want, now actually, okay, so let's take a look at how we have two costs now. The cost for firm A and the cost for firm D. So let's take a look at both of those comparative statics separately. Okay, so I'm taking the derivative of firm A's equilibrium profit with respect to increases in its own costs, right? So that's the derivative there. Now I want to check to make sure that that's still negative. because increasing my cost should hurt my profit. And in fact, that's true. But let's check to see how increasing my competitor's cost affects my profit. Okay, so D. Now, I would expect this to be positive. I would expect that that increasing my competitor's costs will will help my profit. Increasing my competitor's costs will help my profit because it puts my competitor at a disadvantage. And in fact, that is true. Okay. And then let's do the comparative statics with respect to the demand slope. Okay, and let's confirm that that is still negative as it was before. Right. And now the interesting thing is we can do two kinds of interaction effects. We can see, let me just skip the interaction effects with respect to A. And just go to the ones with respect to C. So let's see if the effect of B has an interaction effect with, if B has an interaction effect with my own costs. It does. It looks positive. Let's confirm that it's positive. It is. Now let's do the same thing with the interaction effect of B and my competitor's costs. So I would expect this to be the opposite. D, I would expect this to be negative. So let's check the derivative. There's the derivative. And is it negative? Yes, it's negative, right? So we've gone through the same set of steps for the Cournot equilibrium that we went through for the monopolist. We defined the parameters of the model and expressed our assumptions about them. We defined the objective functions for, in this case, two objective functions for the two oligopolists, the Cournot duopolists. And we derived the first and second order conditions, confirmed that the critical point is in fact a maximum by using the second order conditions. We substituted the equilibrium solution back into the two objective functions. And then we used comparative statics to develop some propositions. Now, I only did the comparative statics with respect to the profit of firm A, but I could also go back and rerun these with respect to the profit of firm D. Do a quick search and replace. I'm just going to search and replace for pi A and replace pi A with pi D. Next. Replace, 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 replace. Okay, so here's the main effects, except that I'm going to need to change the signs on the two cost derivatives, because again, I expect that helping my own costs will increasing my costs will hurt my profit, increasing my competitor's costs will increase my profit. And the identity of the competitor is just the reverse in this case. So I need to reverse those two inequalities. In order to do the simplification, I need to give Mathematica more information about the relationship between, yeah, okay. Sorry. This does raise an important point. Sorry. There is one other assumption I need to impose here. Not just that there's a second order condition satisfied, but I also need to impose the assumption that that both firms produce positive output. Because I've given one firm an advantage over the other firm, it is possible that the advantaged firm could run the disadvantaged firm completely out of business, right? Because of the cost difference. I forgot to take that into account. So if the advantaged firm has such lower costs than the disadvantaged firm that it basically runs the disadvantaged firm out of business, I need to control for that, because I don't want to allow that to happen, because that becomes a monopoly case, right? If the advantaged firm runs the disadvantaged firm out of business, then we're in a monopoly case, which was the other file. To preserve the duopoly, I need to impose the assumption that both firms produce positive output. So let me rewind back here to the outputs. Okay. I can first show you QA equilibrium, place all QA, let's see, solve place, right? Okay, so that just gives me this expression as QA equilibrium. Let me do the same thing for QD. It's fairly trivial to show that under our assumptions, QA is greater than QD, right? That the advantaged firm will produce more output than the disadvantaged firm. But let me prove that. Oops, I made a mistake here. Rerun that. Okay, so this should be QD equilibrium. So let me prove that firm A, as long as our parameter assumptions are satisfied, is going to produce more output than firm D. True, right? So firm D cannot run firm A out of business, but firm A could run firm D out of business. Firm A could put D into a position where its output is negative, basically. We don't want to allow negative output. So what we need to do is we need to add to our parameter assumptions vector. So what I'm going to do here is I'm going to define parameter assumptions 2. And I'm going to add an extra element to the parameter assumption. So I'm going to use the union function, just like a union in set theory. I'm going to take the original parameter assumptions and I'm going to join that to a second set, which consists of let me see. I'm going to, in order to, I would like to get rid of the denominator in this output, because it doesn't play a role in determining whether firm D is producing positive output or not. So let me just simplify greater than 0 parameter assumptions. Okay, so there's the condition that guarantees that both firms produce positive output, so that we have a true duopoly, not just a degenerate duopoly that turns into a monopoly. Okay, so I'm going to add that assumption to my set of assumptions. And see, there it is. It's added into my set of assumptions. So now what I'd like to do is I will replace all the places where it says parameter assumptions with parameter assumptions 2. well, at least down here. Okay. I'm going to add comments. Effects on firm A's profit. This is not changing because firm A is not going out of business under any circumstances in this model. But firm D's profit, I need to make some adjustments here. Okay, so from here on out, I need to change parameter assumptions to parameter assumptions 2. Replace, 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 replace. Okay, good. So now let's run this again. I'm gonna grab all of the cells that I want to run. So they're all have this blue marker on the right, and I hit Shift Enter, and that executes them all. Okay, so now everything turns out as I had hoped, because as long as I have told it, now that I've told it, you have to assume that firm D stays in business. Now I get the results of my that I was expecting. Right now it's saying true here and true here and true up here as well. Right. And so I can now also replicate these interaction effects for firm D. And say interaction effects on firm A's profit. And let me clarify up above that I was doing main effects. Main effects on firm D's profit and main effects on firm A's profit. Okay. So let me come back down here. Okay. So let me copy these. Oh, copy all of them. Copy. Copy those cells. Okay, firm D's profit. Okay. I'm going to do a quick search and replace for replacing pi A with pi D. Next, replacing pi next, replace, 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 replace. Okay, good. Now, of course, I'm going to reverse the signs here because, again, the identity of the focal firm is being swapped with the other firm. So I need to reverse those inequalities. And we get the same results. Okay. So now I'm done. Any questions?
How do you, as you were walking through this, I was thinking about a theoretical question that I'd like answered. And
okay.
And I'm wondering how you would load firm data, like massive amounts of data, into this equation, kind of like coming back to Mita's earlier comment of she has too much data or too little.
Right. Right. So yeah. So for example, if you had some data that would tell us a little bit about the values of the parameters A, B, and C here, right? You could do that in Mathematica. Mathematica can run regressions. You know, in fact, I've used that sometimes when, you know, for a different purpose. I've used that when it's impossible for me to get an exact solution to a model because the model is too complicated and I have to use numerical methods to find approximate solutions. And then I want to derive I want to express those solutions not just as numbers, but as functions. And so I will fit a curve. You know, I'll use a least squares algorithm within Mathematica to fit a curve to be an approximate solution to the excuse me
The parameters.
to the model, right? My paper with Jens Schmidt and Thomas Kyle several years ago in SMJ used that method. So yeah, I mean, Mathematica has so much that it can do, and you're right, it can handle data too. But you know, the unique piece about Mathematica is that it does symbolic calculations, not just numerical calculations. So it's been an honor and a privilege to work with you guys.
Yep, next week. Thank you, Richard.
Thank you.
Bye.